Today I wanted to talk about distributed consensus. Distributed consensus is the problem of how we reach decisions in a distributed system, despite the fact that the participants in the system are unreliable and also asynchronous. What this means in practice is that the servers that make up a system, as well as the clients, may crash, may become unresponsive. The network that connects these machines may drop packets, they may reorder packets, and by asynchrony we mean that we can't even rely on the participants in the system having a shared notion of time, and we can't rely on messages being delivered within a certain bound or participants answering us quickly. This is a fascinating area, and if we can solve distributed consensus, then we can build really powerful, really interesting distributed systems. I'm sufficiently interested in distributed consensus that I did a PhD in this area. My thesis was titled Distributed Consensus Revised, and it is available online. I will put a link to it somewhere or other. So we'll start with what is the problem of distributed consensus. There are two components in the system. There are the proposers. These are a bit like the clients of the system. And there are the acceptors. We can think of these like the servers of the system. The role of the proposers is to propose values to be decided, and the role of the acceptors is to accept some of these proposals. The proposers in the system are the active participants, so these are the participants in the system that are sending messages and they're waiting for responses, whereas the acceptors in the system are the kind of passive participants. So they're like servers, they're there, they'll answer requests when they receive them, but generally they just sit there and they run. Input to a proposer is a candidate value. So this is the value that that proposer would like to be decided. And the output is the decided value. So if the proposer is lucky, the candidate value which is put in will be the same as the output, be the same as the decided value that's outputted at the end. However, this isn't necessarily the case. So for example, if a proposer had already written a value and a decision had already been made, then the proposer will find out a different decided value from the one that it's proposing. The role of the acceptors in the system then is just to basically store this decided value. So what separates distributed consensus from other distributed agreement problems is the three requirements of distributed consensus. The first is non-triviality. This is the requirement that the decided value must have been proposed by some proposer. So this rules out solutions where, for example, whatever happens, the servers just always answer 43 to whatever the question is. So our second requirement is safety. Safety says that only one value must ever be decided. So this stops our acceptors, for example, from just echoing what each proposer says back, because different proposers would then learn different values. And thirdly, and perhaps most importantly and interestingly, is the progress requirement. So this says that eventually every client learns the decided value. So this means if the system is live, if the servers are up and they're responding, and the network is delivering messages for us, then the client should learn the decided value. Okay, so to start off with, let's come up with a really simple algorithm. We're just going to use a single server. So here's our single server. We're going to name it server 1. And we've got a client that's coming along here, client 1, and the client has an input value, which is A. The client's going to send a message to the server. This message is called a propose message, and it includes the value A. When the server receives this propose message, it's going to write the value A into its persistent storage, and then it's going to respond to the client with the message accepted A. The client's now learned that the value A has been decided, and therefore it's going to output A. Now another client, in this case C2, is going to come along. This client has the input value B. It's going to send propose B to the server, just like client 1 did. However, this time when the server receives the message, because it's already written a value, it will respond with accept A. And so in this case, the client 2 learns what the decided value was, but the decided value is different from the value that it proposed. At the end of this, both clients learn the same output value, which is A. Let's have a look at the requirements of consensus from before. So we can see that this algorithm satisfies non-triviality because the decided value is a value that was written by one of the proposers in the form of the proposed message. We satisfy safety because both clients learn the same value. And we satisfy progress because every client, in this case C1 and C2, learn the same decided value when that server is up. Great! End of story, consensus solved. Unfortunately, it's not as straightforward as that. Consider a third client, C3. C3 comes along and has the input value C. They send proposed C to the server. Unfortunately, the server has failed, and the client 3 is sadly left waiting for a response. What we'd really like to be able to do is to use multiple servers instead of just using one server, and try to reach consensus using those, such that we could tolerate a failure. So let's make an attempt at doing a multi-server solution. This time we've got 3 servers, server 1, server 2, and server 3. And we're going to try applying the same simple algorithm as before. Client 1 comes along. Client 1 has the input value A. And client 1 sends the message to server 1 saying propose A. When server 1 receives this message, it writes the value to its persistent storage and responds to client 1 with accepted A. Client 1 can now safely output the value A. Now client 2 comes along, and client 2 has input value B as before. Client 2 is going to send propose B, in this case to server 3. Server 3 is going to write B to persistent storage and respond with the message accept B. It's now the case that client 1 and client 2 have learned different output values. So if we revisit the requirements of consensus from before, we still have triviality. We no longer have safety because the clients learned different values. We do, however, still have progress. So how can we avoid problems like this? Instead of requiring clients to write the value to one server, we're going to require them to write it to 2 of 3 servers. The good thing about using 2 of 3 servers is that any pair of servers in a set of 3 is going to overlap by at least 1 server. Let's have a look at this in practice. So as before, we've got 3 servers and we've got our client C1 who's going to send propose A to the servers. Because we're using our new algorithm, the client needs to wait to get accept messages from 2 different servers, in this case server 1 and server 2. Once the client receives these messages, it can output the value A. Now a different client's going to come along, client 2, and they're going to send propose B to server 2 and server 3. Server 3 is going to respond with accept B, but server 2 is going to respond with accept A. This means that server 2 isn't able to learn which value has been decided unless it waits for a response from server 1. In fact, that's not the only problem. It actually gets even worse in practice. Imagine again that we have 3 servers. Client 1 is going to send a message to server 1 proposing A, and server 1 is going to write the value A. Client 2 is going to write the value B to server 2, and client 3 is going to write the value C to server 3. We now have a deadlock. Because the servers don't overwrite values, we're not going to be able to reach consensus at all. If we go back to our requirements for consensus, we can see that we do have non-triviality and we do have safety, but we don't have progress anymore because we can reach this state where we're basically in a deadlock and we're not able to reach a decision. So that's everything I wanted to cover today. At this point, we've seen a solution for a distributed consensus with 1 server, but we've not yet been able to get a solution that works for any number of servers. Next time, we're going to look at the Paxos algorithm. This is the Turing Award-winning algorithm that solved this problem, but is famously difficult to understand. Thanks for watching.